Hi, hello. My name is Cassio, Oishi, and today I will be talking about nonlinear parametric models of viscoelastic fluid flows. This is a joint work with Alan Kaptanoglu, Nathan Kutz, and Steve Brunton. Okay, first, let's talk about reduced order model in fluid mechanics. We have like this big picture. You select your flow, canonical or a benchmark flow or benchmark geometry, and then after your simulation, you capture the snapshots. Using a dimensionality reduction, you can analyze some information in terms of your dynamic. For example, you can obtain a simple representation of your dynamic using the temporal coefficient. This is classical POD Galerkin projection. Okay, more recently, we have incorporated machine learning and deep learning strategies to construct more sophisticated reduced order model. In this case, data-driven reduced order models are widely applied in Newtonian fluid mechanics. In our work, we are interested to extend this idea for non-Newtonian fluid mechanics. Basically, we selected one type of non-Newtonian materials, the viscoelastic fluid. We applied a sparse identification of nonlinear dynamics, the SINDy algorithm, to construct a data-driven model, a sparse data-driven model, where we can include information about the parameter. Then this is a fully parametric nonlinear model. But what are non-Newtonian fluids? We have some information using these plots, but basically, many materials behave as a non-Newtonian, like, for example, real materials, as, for instance, the blood, some foods, oil, and paint. And when you look for the plots in this slide, you can observe, for non-Newtonian materials, a nonlinear relation between, for example, the viscosity and the strain rate. Therefore, it's important to simulate this class of flow and compare with Newtonian one. For example, this is a very classical benchmark or setup. This is rod climb effect. We have on the left the Newtonian fluid. On the right, we have the viscoelastic one. You can observe for Newtonian, the fluid is dipping, while for non-Newtonian, the fluid is climbing the rod. Therefore, simulations of complex materials, like, for example, viscoelastic flows, the simulations are very expensive, and then it's important to think or to construct reduced order model in order to have more information about the dynamics in this complex situation. Okay, we start our work using a very simple geometry, a square, okay? Just as an illustration, we have some simulations and I include in the plots. For example, we have the first column, low values for Weissenberg number. In other words, we have the flows where you observe a laminar behavior or just a steady behavior if you capture the information of the stress tensor in the center of the domain. But in the middle, you can, if you include more elasticity in the system, you can observe a transition from the laminar to one oscillatory regime. And if you continue increasing the elasticity in the flow, you can see a transition from this oscillatory regime to a chaotic one. If you construct a map varying the parameters in our simulation using this geometry, the 4-row mu benchmark, you have two parameters because we are using a simplified viscoelastic model, the Oldroyd-B. If you analyze these parameters, if you change the values of these parameters, the Weissenberg number and beta, you can analyze transitions from steady to oscillatory and chaotic. Therefore, this geometry is very simple, but you can analyze some transitions, some bifurcations, and also the presence of the elastic turbulence just using this geometry. Full order model, we have some equations where we are interested to simulate, to capture the snapshots. We have the mass and the momentum equation. It's important that we are highlighting the non-Newtonian contribution on the momentum equation. We are using the Oldroyd-B fluid, as I said, and then we have one constitutive equation for the conformation tensor. The tensor denoted as letter C. You can apply the decomposition and obtain information on this matrix B. There is a square root matrix. It's important to mention that C is a symmetric positive definite matrix, and then you can apply this decomposition. In terms of non-dimensional parameters, we have the Reynolds number in the equation, we have the Weissenberg, as I said, is related to the elasticity, and you have beta. Beta is the ratio between the viscosities on the system, the solvent viscous and the polymeric viscous. But in this work, we just analyze one parameter in our reduced order model. We fixed beta, and we investigate the influence of the Weissenberg number. It's important because the Weissenberg number is related between the competition, between elastic and viscous force. Okay, first step in our algorithm is to produce some information about the tensor B. And then we apply the proper orthogonal decomposition. And you capture snapshots at the time. Okay? We are just using the tensor B because we are considering low Reynolds number flows. And then the velocity in this case is not considering to extract the data. If you look for the POD modes, the spatial modes, and the temporal coefficients, you can see some variation in the space for the first to the second and the third mode, and also this oscillatory behavior for the temporal coefficients. Okay? More information about the pair trajectories. We have the first 5 temporal coefficients in this simulation, just to confirm that we are, for now, we are considering just one oscillatory regime. Our algorithm is based in the SINDy. You know, SINDy is a data-driven framework and can help you to produce sparse, reduced order model. More details about SINDy framework, you can check the videos on the Steve Brunton channel. In our work, we have extended the idea of the SINDy because now we are considering some information about the parameters. For example, we extend the dictionary, the library. We are using now the temporal coefficients and also one part to represent the parameter of the flow, where now we are using the Weissenberg number. It's important to talk now, in this moment, that we are just using the first 2 temporal coefficients to produce our reduced order model using the viscoelastic data. Okay, this is the main part of this conversation because now this is the dynamical system that we can produce using the SINDy algorithm. Observe we have one part related to the linear part, and we have one additional part, this is letter T, is related to the cubic terms, okay? But we can apply these terms for a fixed parameter, or if you are using a parameterized system, observe we have a more complex term. But now we have the parameter inside the system. Okay, I don't have time to talk about stability details, but you can check in our preprint some analysis about that our model is stable. It is very important to simulate using a reduced order model. Also, you can check some structure in terms of the coefficients on that matrix. Therefore, we are including some interpretation of the system, looking for these coefficients for the fixed parameter, or if you are using a parameterized system. Finally, we use the first 2 modes to construct a relation for the third and the fourth modes. using this sparse algebraic relationship. All details you can check in our preprint. Let's talk about results. Now we are plotting the trajectories for the first modes. And you can see a very good agreement between data and our response of the reduced order model. In addition, we plot the energy on the system, the energy on the temporal coefficients, the letter k, where k is the Lyapunov function, as a function of the time. And you can, looking for this picture, just to confirm, the system is stable when you just include the first modes in our analysis. Okay, it's important talking about reconstruction. If you look, now I am just considering one component of B matrix, the square root tensor. For this component, you can see that we have low error in terms of reconstruction. Observe that the maximum error in this case is lower than 2%. And then this is another important point in terms of our reduced order model. If you look for the reconstruction as a function of the time, for example, in this case, we are plot the trace of the conformation tensor. You have the SINDy, or a response of a reduced order model, and the data. You can see a good agreement. In other words, we can capture the main signatures of the flow using a very reduced order model, like a sparse reduced order model. And then we can gain in CPU time, because to solve a reduced order model, it's very simple compared with a full simulation in this case. Finally, we analyze our results for a parametric model. Okay, we have two values for training data, where these values for the Weissenberg numbers are related to an oscillatory regime. If you look for the interpolation, highlighted in yellow in this slide, you can see that, okay, you can capture results using the interpolation data. But also, it's important to mention, if you increase the Weissenberg number, high values, for example, for the Weissenberg number, you can use this to after the training just to testing for extrapolation value of the Weissenberg number. This is highlighted in purple in your screen. And then you can see increasing the elasticity. You can apply the reduced order model, and you capture in good agreement when you compare the data and the response of the SINDy model. We also applied for a higher Weissenberg number. It's a very complicated benchmark when you increase the Weissenberg number, because you have more chaotic behavior or aperiodic. And our system can capture, our dynamical system can capture the temporal behavior. Also, if you look for the energy on the system, the energy is kept like, okay, you have the stable strategy. Okay, now some conclusions of this work. First, it's important because we have applied for a simple geometry for just one viscoelastic model, first steps to construct a data-driven reduced order model. But it's important to mention that we have used a parameterized strategy. In other words, now our model is able to capture the variation of the parameter. In addition, we can, according to our results, the prediction, the time prediction, and the prediction in terms of dynamics, the predictions are a good agreement with the data. And also, we observe that good quality in the reconstruction of the flow. We have some limitations and then some motivation for next steps. First, we needed to improve our strategy when we are going to elastic turbulence or more chaotic dynamics. Also, we needed to incorporate more complex non-Newtonian models or non-Newtonian equations. And finally, it would be very important to investigate new geometries or new benchmarks in non-Newtonian fluid mechanics. I would like to thank our sponsor and your patient. Thank you.